In this video, we're going to introduce the topic of related rates. So this one, we're just going to kind of introduce it, and we'll do more examples in future videos. So these related rates are all going to be related to time. So as time is progressing in some scenario, oftentimes several different quantities are going to change. We're going to call these related rates because they're changing. They're rates, but they're related because they're all like in the same scenario, and they're changing because another one is changing. So here's just one common example. If you open up like a textbook, almost all the time you'll see this picture of like a balloon blowing up. So just imagine we have this balloon and you're blowing air into it, so it's getting bigger and bigger. So as you're blowing up, as time's going on, right, the amount of air in the balloon is increasing, right? The amount of air in here is going. The volume of the balloon is increasing, right? It can hold more air. The surface area of the balloon is increasing, right? There's more stuff on the outside of this balloon. Right? The radius of the balloon from the center to the outside is increasing. Right? The air in your lungs is decreasing. Right? A lot of other things are increasing, but the air in your lungs, right? You're blowing the air into the balloon, so that's going down. And your desire to keep blowing up a balloon is also decreasing because you're getting tired of blowing up this balloon. So all these different quantities are either increasing or decreasing or changing, all by just this one scenario of putting air into a balloon over time. All right, another kind of simple example. If we look at this Desmos thing, we have a circle, and I can kind of change the radius. So we start off with a radius of 1. We can see the area and the circumference. The area is smaller than the circumference. All right, different units because this is units squared and this is units, but area is smaller than the circumference. But as I increase the radius, you can see they're both changing, all right, because the radius is increasing. And now you can see the area is actually bigger than the circumference, and as we go farther, now the area is much bigger than the circumference, so they're changing at different rates. The circumference is kind of slowly increasing while the area is kind of rapidly increasing. They have different rates as they change. An important thing to remember is that time is causing all the movement in these scenarios. Our actual input that's changing is time. So there might still be x's in the problem, but the actual input, the thing we're actually talking about, the change happening with, is time. So what does that mean? So just say we are not looking at a scenario here. We're just going to look at this equation and just say x and y are kind of changing with respect to time. How would we figure out the rate of change with respect to time? Well, normally when we do a derivative, we have like dy dx. This means the change in y. So the little d means change over the change in x. But we're talking about little changes in time and figuring out how those values are changing. So we want to find things like dx dt. How is x changing with respect to time? Versus how time is changing, and same thing with dy dt. So when we do this, it's basically like a mini chain rule problem. We take the derivative of x, we just get 1. But the chain rule says I have to take the derivative of x with respect to time. Because time is kind of the thing we're doing all these derivatives with. Derivative of 3y is 3. Derivative of y with respect to t. The derivative of 5 is 0. All right, so this is really the only main thing I want you to get from this video is these dt's here. All right, the time is the thing that's changing. Those are the little segments of change we're looking for. All right, so they're always going to be on the bottom of these changes. All right, so the important thing to remember is that when doing a related rate, you're taking the derivative with respect to time. So every other variable, and time's not normally in the equation, so pretty much every variable is a little chain rule where you take the derivative of the thing normally, and you have to put that like dx dt at the end.